Welcome back. Today we're going to talk about accumulation functions, which I know it's a name that maybe you haven't heard before. You know about a lot of functions like polynomials, rational expressions, exponentials, logarithmic functions. But what is an accumulation function? Well, these functions are very common, and I'm going to tell you why they are so common. Um, and let's start by telling you what they are. An accumulation function is a function defined in terms of an integral. It always has a constant as one limit of integration, and then your variable, the variable for the function is the upper limit of integration, typically. Um, so that makes this function unique. Every other function you've learned of is not in terms of an integral. And this accumulation function, what it does is it tells you the area that you accumulate if you start at your constant a and you keep going up to some number x. That's where the name comes from. It comes from counting, gathering all this area that you build up in going from a constant to some variable, which typically is a constant or a value that happens after or to the right of a. Um, you have seen these questions or these type of problems before, especially with functions that have that are piecewise curves that have shapes that you can easily integrate, like a rectangle, a triangle, or a semicircle. And the fact that an accumulation function is related to an integral is not the only reason why they are common. They are common because the fundamental theorem of calculus is defined in terms of an accumulation function. You probably remember this. I hope you do. And when you take the derivative of this type of function, the derivative is just the function inside the integral, because remember, an integral, what it does is it takes an antiderivative. So if you take the derivative of the antiderivative, they cancel and you end up with the function inside. So this is why accumulation functions are so common, because not only do they provide you with a chance to do integrals, but then you can analyze them easily in terms of their derivative. And what I mean by easily is that the derivative of the function itself, of the accumulation function, is the function inside the integral. Well, let's take a look at an example, an AP question from a past exam that has an accumulation function. Here, our function is defined in the interval that goes from -4 to 3. Note that it is continuous, and the part of the function that looks like a circle is indeed a semicircle center at the origin. If you look at that semicircle, its radius is 1, which is good to note. And here is our accumulation function, which is given by the integral from 1 to x of f of t dt, where f of t is your function that is graphed here on the left. So the first question is asking you to find g of 2. So let's plug in and think about what this is. What is this? The integral from 1 to 2 of f of t dt. Well, that's an area. It's the area between your graph and your x-axis, which is right here. Now, we can easily find that area, right? The area of a triangle is half base times height. Our base here is 1. You can see that there. And the height, well, since the radius of the circle is 1, this has to be -1. So that seems to be about half. So we're just going to make an approximation and call it half. So then this will be 1/4. I'm just thinking if we can justify that this is half, and I guess, yes, you can. Because this is a straight line, then the slope here should be the same as the slope there. So 2 over, 1 down, and then 1 over, half down. That makes sense. So, yep, that is a half. So let's move on and find g of -2. So now we're going to plug in -2 as our upper limit. And before I do the integral, remember that we like to write integrals with limits of integration that are increasing. So we want to switch these two, and you want to do that, otherwise you might make a small mistake that's going to cost you a few points. But more importantly, well, it's not going to show that you understand this 100%. So we want to flip those limits of integration. And remember that when you do that, you introduce a negative sign. That's one of the properties of your integral. So then we can now say that this is the area that starts at -2 and ends at 1. So it's this area here. And we're going to take the negative of that area. So we have a triangle of of height 3 and base 1. And we have a circle, actually a semicircle, which means we're going to divide this by 2. That has a radius of 1. The area of a circle is just pi r squared. One more thing we want to note here is, first of all, we should use parentheses around the whole thing because we're taking the opposite sign. Then the area of the triangle is positive because it's above the x-axis, but the area of the circle is negative. It's below the x-axis. So then what we're going to get here is 3/2 minus pi/2, which after I distribute the negative will end up to become pi minus 3 over 2. Alright, so that is it for part A of this question. Ready for part C? I got confused because I had part B here. That was still part of part A. Sorry, let's do the next part. Part B. Alright. What is the derivative of g, our accumulation function, at -3? And what is the second derivative of this function? Well, start by writing the function again. Here is g of x. And then let's write the derivative of g of x. And according to the fundamental theorem of calculus, the derivative of this function is just f of x. So then it's very easy to figure out what's g prime of 3 because all it is, it's f of 3. And f of 3, I can read it from the graph. When x is 3, whoopsie, that's -3. When x is -3, I should slow down What is the value of x? Let's see. The value of your function f when x is negative 3 is 2. Alright, that wasn't too bad. It was barely an inconvenience. Alright, so let's do g double prime of negative 3. How do I get that second derivative at negative 3? Well, first of all, slow down. What is the second derivative of g? Well, since the first derivative of g is f of x, then the second derivative of g is the first derivative of x. Does that make sense? Yep. This is just taking the derivative of a function. The derivative of f is f prime. The derivative of g prime is g double prime. So, how do we get f prime at 3? Because that's what we want. I keep saying 3. I meant negative 3. Alright. I'm going to stop that. What is the derivative of f at negative 3? Well, the derivative of a function means its slope, or the slope of the tangent. Lucky for us, this is a straight line, so we can get that slope very easily. What is the slope of that line? So, we go up from 1 to 3, so that means we are going up 2. And we go from negative 4 to negative 2, so we're moving to the right 2. So that slope is 1. So the second derivative of g at negative 3 is 1. Alright, let's move on. Let's see what else we can do with this type of function. Now for part C, finally, they say, where do we find the points where g has a horizontal tangent line? And then classify it as a relative min, a relative max, or neither. Justify your answer. Okay, so how do we know when a function has a horizontal tangent line? What does that mean? Horizontal tangent line means that something is 0. It means that the derivative is 0. So the derivative of the function g is just f of x, right? We just saw that. This is the fundamental theorem of calculus. So when is f of x equal to 0? Well, that's just every point where the line touches the x-axis, right? So at least there's one point. Here's another one. So there are two possible points that can be relative max or mins, or we would call them critical points. How are we going to determine if these are max or mins? Well, we need to find the sign of your derivative. The sign of g prime, right? But remember, the sign of g prime is basically the sign of f of x, right? G prime and f of x are the same thing. So to the left of negative 1, the function is positive. To the right of negative 1, between negative 1 and 1, the function f of x is negative, which means the derivative is negative. The derivative of g is negative. And then, once again, if I keep going past 1, the function is also negative. Alright, so then, what does the derivative tell you about a function? So if g, this is a graph for g prime of x, right? So if g prime of x is positive, that means g of x is increasing. When it's negative, it's decreasing. So what you see here is that your graph is going to do something like this, right? And we only see a relative maximum at negative 1. So we have horizontal tangents. At negative 1 and 1, x equals negative 1 and 1, and relative max, sorry, I'm rushing through this, relative max at x equals negative 1. Hey, let's keep going. Let's do the last question before we end. All right. Now what they're asking you to do is to find all the values of x where we have points of inflection. So to find points of inflection, we need the second derivative. We need to look at the second derivative of g, which is the first derivative of x. And we are looking for points where the second derivative is 0 or undefined. In the previous problem I uploaded, we did not see points that were undefined, and I forgot to mention that. But a point of inflection can also occur when a second derivative is undefined. So, to say here that g double prime is 0 or undefined, it means that the slope of the graph is 0 or undefined. So you gotta make that link that the second derivative of the function you're analyzing is related to the first derivative of the graph that you're looking at. Okay, and in other words, it's related to the slope of this graph. So, when is the slope of this graph 0 or undefined? Well, the slope is undefined here because we have a corner. And it's also undefined here for the same reason. You can call that one guy a cusp. And we have another one here. Oh boy, there's plenty of possible inflection points. And there is one point where the slope is actually 0. So we have 4 possible points of inflection. So that's the first condition. The slope at a point of inflection. Sorry, let's try that again. G double prime has to be 0 or undefined, and in this case, it means that the slope of your function f, which is f prime, has to be 0 or undefined. So that's negative 1, negative 2, let's try that again, negative 2, negative 1, 0, and 1. And the second condition for your points of inflection is that the second derivative is changing signs, right? So, in this case, to know what the second derivative is doing, we're looking at the slope of our function. So to the left of negative 2, the slope is positive. Your function is going up. Between negative 2 and 0, the slope is always decreasing. Aha! So then, this guy is not going to be an inflection point because the second derivative is not changing. Okay? And then between 0 and 1, then the slope is increasing. The function is increasing, which tells you the second derivative is positive. And finally, from 1 to the right, this function is decreasing, which means its slope is negative. And again, the slope of this graph is the second derivative of g. So how many inflection points do you see? Well, there are 3, right? We got one here at negative 2. We got one more at 0. And we have one more at 1. So those are your inflection points. Inflection points occur at -2, 0, and 1. Phew. Hey, we're done. So now you see a lot of the type of questions you could get for a cumulative or an accumulation type of function. And with that, we'll finish our video for today. Hope this was helpful, and I'll see you next time.